Well, thanks, John, and thanks everybody for attending. So, as John mentioned, I'm a software engineer in Research Applications Laboratory in the National Security Applications Program. My main focus over there in RAL is in GPU accelerated large-eddy simulation model development and application. So today I'll talk about that topic using FastEddy model developed here at NCAR. So just a real quick acknowledgement to my collaborators in this work, Domingo Munoz-Esparza from the RAL Aviation Applications Program, and Alessandro Fanfrio, who is also in the National Security Applications Program, along with me. Contributing stakeholders and sponsors, Defense Threat Reduction Agency, RAL Opportunity Award, the U.S. Army Test and Evaluation Command, and Uber Technologies. So, first up, I'll just give a little bit of a goal and an outline. My hope here is to provide an update on some milestones and capability additions in FastEddy that might inspire future collaborative efforts on using GPUs for modeling, analysis, and visualizations that help benefit science and society. So a simple outline, I'll give a bit of background about FastEddy itself. Then I'll get into the meat of the talk where I'll sort of meander around FastEddy progress over the last year, from verification and validation exercises to physics and numerics extensions, performance assessments, and performance enhancements. And at the end, I'll hope to close with a compelling bit on filling a gap in forecasting. So, a bit of background. It turns out that just over a year ago, I was in this very same room giving a CISL Work in Progress seminar on FastEddy. It was always intended to be a GPU accelerated modeling capability. And at that time, you can see we actually had more contributors. We've lost a couple to the sunny climb of San Diego and one to upper management, but we had fewer sponsors, so that's a good sign. We have more sponsors now. So at that time, I would have mentioned what I mean by accelerated simulations. So a simplified view of simulations, I would consider them to just be algebraic recipes. You take physics laws, you write down some conservation equations with calculus, you turn that into some algebra, and you do it on a computer. This could be for the atmosphere, the ocean, or economics. It doesn't really matter. But what we see most often here is Newton's laws turned into Navier-Stokes equations. Then you use some numerical techniques like Runge-Kutta or finite differencing or spectral methods to get some algebra, and that turns into models like MM5 or WRF or IMPASS or FastEddy. So a simplified view of acceleration is really just trying to exploit some hardware or software technology to execute that recipe of algebra and arithmetic faster and more efficiently. So that boils down to mostly two things. If we think of this simple equation down at the bottom, the red oval is the arithmetic. We typically talk about that in terms of floating point operations or flops. And the blue arrows might designate pulling out of memory the values in X and Y, and then computing, making the computation, and putting the result back in memory. Now that data movement is typically described by bandwidth. And so with simulations, it's really just a question of running through memory, doing that over and over again as fast as possible. There is one more cost to think about, and that's latency. And so we might think of that as sort of a penalty or the extra time it takes for us to ask a question and for that, or make a request to data, to memory, to have data pulled in, and then the time it takes to respond. A little more background on why did we decide to do a GPU accelerated model. Well, the trend has been for quite a number of years, almost more than a decade now, GPU computational power in terms of flops and peak memory bandwidth have been outpacing CPUs for quite a while. So this is a slide I've adapted from one that was in a keynote at Supercomputing 2015, I believe. And we can see the exponential growth is the GPUs, and the blue lines are the CPUs. I added some markers to designate what kind of our previous machines here at NCAR looked like. So the yellow circle would have been Yellowstone with the corresponding DAV partition, the data analysis and visualization partition, made up of Caldera, which had K80s on it. And then as we moved into Cheyenne, we got much better in the CPU. And Simbox was a GPU machine that we purchased in RAL so that we could start writing a GPU Large-Eddy simulation. What are CPUs good at? Everything. CPUs are good at everything. Control, device management, logic operations, arithmetic, moving data around. GPUs are really good at arithmetic and data movement. That's it. They're purpose-built to do math really fast. So what is Large-Eddy simulation? It's these specific equations. I had to throw some equations into the talk. It's really about high Reynolds number flows under three-dimensional Navier-Stokes conservation equations, the first being for mass, second for momentum, and the third for energy. We don't do as many parameterizations in Large-Eddy simulation because we're looking to do turbulence resolving scenarios where we model at very fine scales because we want to be in the isotropic range of three-dimensional turbulence. So the only parameterizations we would have in an LES are for subgrid scale forcing from unresolved turbulence and surface layer effects. So also at that time, a year ago, I would have given some background information on the salient characteristics of FastEddy. It's a built from scratch code, C, MPI, and CUDA. At the time, it was about 6,000 lines of code, and the MPI was there for future scaling across multiple GPUs. But a year ago, we were on a single GPU. It's built as a resident GPU algorithm, and what we mean by that is that all of the computation, all of those terms in the governing equations are solved on the GPU. We want the data to live down there and the next state of the data to stay on the GPU. This allows the GPU to set the pace of simulation progress rather than waiting on the CPU, and it minimizes data traffic between the CPU and GPU. So some of the initial physics and numerics of FastEddy, it's a dry dynamical core, so at this time there's no water vapor or microphysics. It uses finite differencing over a generalized Cartesian coordinate system. We have multiple time integration schemes, but it is explicit in time, first through third order Runge-Kutta. We have multiple advection schemes, so we can dial up the order of accuracy of advection from first to sixth order. We use a Lilly-Smagorinsky turbulence closure scheme, and at this time we have a diagnostic eddy diffusivity as opposed to a prognostic TKE-based eddy diffusivity. And then we add in some auxiliary scalar transport and dispersion. So, at that time, 1 year ago, on the work in progress, we had just performed our first full atmospheric boundary layer simulations, or at least simulations we could call an atmospheric boundary layer. On the left, we're seeing a neutral, a vertical plane, XZ plane, in a neutrally stratified ABL, and on the right, a convective one. It's a little washed out, but underneath, we see the development of the mean profiles with zonal and meridional velocity, followed by wind speed, density, and potential temperature for each of the scenarios. And then I would have given a little bit of a glimpse at some of the turbulence statistics we were starting to look at. Because again, when we're doing large-eddy simulation, what we're interested in is resolving turbulence. And so turbulence characteristics become an important measure of the model and how well it's doing. So that's where we were at about a year ago. Oh, one more. We had some promising performance. So what we're looking at is a Google Earth image of Boulder, and that is a domain, I want to say, yeah, it's 25 square kilometers at 20-meter resolution. So it covers about 2/3 of Boulder, and that was just there to give folks a point of reference just to how much area we were trying to simulate at 20-meter resolution. The scenario had a depth of the atmospheric boundary layer of 1.2 kilometers, and that amounted to about 4 million grid points in the simulation. So the FastEddy execution time on the NVIDIA Pascal GP100, which is sort of the penultimate generation of GPU at this point, was 0.023 seconds per time step. FastEddy is a fully compressible large-eddy simulation, so we are explicitly constrained in the size of time step we can take by numerical stability factors or the Courant-Friedrichs-Lewis condition, CFL constraint, to 0.05 seconds. So what that means is, even as a fully compressible code, On one GPU, we could do that much space at 20-meter resolution, almost twice as fast as real time. So that's very promising performance for one socket, so to speak. We acknowledged at the time that there are other techniques you can use, like time splitting methods, that could further relax that CFL constraint, so we could take a larger time step in the same amount of time, or a little bit more, and make some gains on being even faster than real time. But again, a year ago, on a single GPU, we were twice as fast as real time over a pretty sizable expanse on one GPU. Okay, so what have we been doing in the last year? Well, as I mentioned, FastEddy was built from scratch. And there's a trade-off for building a model from scratch as opposed to porting a legacy well-known model to GPUs. That trade-off is we have to prove that it works all over again, starting from the beginning. Even if we're using the same types of numerics, we need to go through a verification and validation process, and that can be lengthy. So in this last year, we've dove deeply into our sort of canonical stability regime cases, being neutral and convective boundary layers. So you're looking again at a neutral case on the left, convective case on the right. You can see sort of shear-driven turbulence characteristic of a neutral boundary layer in the left panel, whereas you have more buoyancy-driven turbulence, very different nature to the turbulence you find resolved in the simulation on the right in the convective case. As part of these explorations into our stability regimes and verification and validation exercises, we want to look at turbulence spectra, which will tell us essentially for a given size of eddy, if you will, how much energy content is there. For the neutral boundary layer case, we're typically comparing against theory. That's where all the theory was developed on what turbulence should look like. And so when we're looking at our neutral regime and doing verification and validation, we're comparing against theory with spectra and higher order turbulence metrics on the right, like correlations and variances. And things are looking pretty good. For the convective case, we've identified some work that was done in a fairly homogeneous expanse near Texas Tech in Lubbock, Texas, where there was a nice tall tower, and we can compare directly against observations for those cases. So the last stability regime, and really the hard one for LES, is stable. And what we used as a basis of comparison for our verification and validation exercises here is actually a publication from back in 2006 where there was a model intercomparison for Large-Eddy Simulation trying to do the stable regime. One of the reasons the stable regime is so difficult is because the size of eddies that are present in a stable atmosphere are much, much smaller. This is because stability tries to damp out turbulence. And so what you find is capturing the proper range of eddy scales and the turbulence cascade across those scales is very, very difficult for LES. You really have to push your LES to very fine resolution spatially and temporally. So as of now, our initial results show a reasonable agreement with mean wind speed profile. So on the right-hand dual panel figure, this is on the left, and potential temperature profile on the right. So ours is the blue line, FastEddy's the blue line. The other black lines are the 6 of the models used in the intercomparison back then. So while we're showing reasonable agreement, we think we may have some sort of some detrimental effects from the fact that our turbulence closure scheme uses a diagnostic eddy viscosity. That lack of sophistication could lead to difficulty in maintaining those fine scale structures that are so important to the stable regime. So that's something to push for moving forward. So some other progress we've made in this past year. Physics and numerics extensions, and in particular surface forcing. So in the 3 stability regimes I described earlier, we're forcing the temperature at the surface, or we're forcing with a prescribed heat flux, an amount of heat that we're saying comes off the ground. Well, in reality, the heat flux is not really constant. It's continually evolving throughout the diurnal cycle. So it was important for us to put in a skin temperature formulation that allows us to prescribe surface heating that's more realistic, like a diurnal cycle. And so what that results in is in cases like on the left here, we have a strongly convective boundary layer where the surface heating is very strong and the turbulence generation is dominated by the buoyancy more than the shear. Whereas on the right, if we started to allow that surface temperature to cool a little bit, we'd transition into a convective roll regime where the buoyancy is not dominating quite as much. So this is key toward in moving away from idealized simulation scenarios and towards more realistic ones. Another important aspect of that is that when we're looking at transport and dispersion scenarios, which is what one of our primary stakeholders' main interests would be, we can see that the different surface forcing conditions on temperature produce very different plume dispersions. So the colored contours here are of a concentration of a passive scalar, and what we see is very different plume structures depending on the surface forcing conditions. This is definitely expected, and this is just another example of why we need additional surface forcing conditions. So some additional progress is centered around the topic of inflow turbulence generation. So up here on the left, when you have a global model, you have no lateral boundaries. The domain wraps all the way around the globe. And so there's no need to specify lateral boundary conditions. Now, that being said, those models are at resolutions, very, very coarse resolutions. Well, coarse relative to Large-Eddy Simulation. Order 10 cubed meters, so order kilometers at best. As we get into numerical weather prediction models, like, say, WRF or IMPASS, they may have domains that span a couple thousand kilometers, but again, their resolution is at the scale of 1 kilometer. And so in these numerical weather prediction codes, they're trying to capture synoptic weather conditions and things like the diurnal cycle so that they get the majority of weather patterns correctly. But in the Large-Eddy simulation world, we're interested in three-dimensional turbulence. And it turns out that there's sort of a space in between where large mesoscale weather prediction models can't produce turbulence because it would, they run at too coarse a resolution. And Large-Eddy simulation models, which do produce turbulence and count on turbulence, can't be run on sufficiently large domains to capture synoptic weather patterns. So if we wanted to couple mesoscale to microscale, we've got to find a way to bridge that gap. It turns out that my colleague over in RAL, Domingo Munoz-Esparza, has been working on this problem for quite a while. And so here on the right, what we have is an example of trying to couple an idealized mesoscale simulation to a nested LES simulation. So again, mesoscale being at such coarse resolution, you see no turbulence. The solution looks very, very smooth because there can't be any development of turbulence on such coarse resolutions. Now, if you'd like to supply an LES boundary condition from the mesoscale simulation, you've got to find a way to spin up turbulence. Here on the bottom, what we have is a reference LES simulation where the boundary conditions are periodic, and you can run that for long enough that turbulence will kick up and you'll reach sort of an equilibrium state to the turbulence characteristics, much like the verification and validation scenarios I was showing you earlier. On the right is what we see when an LES is nested inside of a smooth mesoscale simulation with no turbulence inflow generation. Basically, the fetch required to produce any sort of turbulence whatsoever makes it computationally prohibitive. So what Domingo and his colleagues came up with is an approach called the cell perturbation method. And what they do is apply stochastic potential temperature perturbations to a region on the inflow boundaries that sort of kick up and instigate resolved turbulence within the LES domain. So what manifests is rather than smooth conditions propagating through the domain until finally something starts to kick up, is you get very rapid instigation of resolved turbulence. And this is very important for limited area domain models. particularly LES, where you want to do, let's say 25 square kilometers, most of the Boulder area, or maybe even the Denver area. You need a way to kick up that resolved turbulence. So what we see here is why or I should say, the evidence that the cell perturbation method works so well. These lines on the left are showing with increasing fetch, the color scale, and this is again the energy spectra, and we can see that within certainly by the third line in, the energy spectra looks the way it should relative to the periodic reference simulation. So you get this accelerated transition to develop turbulence. That's key. In addition, the cell perturbation method causes the model to find the right balance between resolved turbulence and mean flow such that it achieves the mean profile that was driving it by some distance into the domain. So that's the methodology. At this point, we've implemented this inside of FastEddy. And here's just a little video of that happening. So this is the cell perturbation method in action. Again, the boundary conditions here are just a smooth, homogeneous profile from something like an idealized mesoscale forcing condition. And we can see that the temperature perturbations kick up this resolved turbulence quite nicely. We judge that in reference to a periodic domain simulation, and we can see that the turbulence structures are quite similar. We obviously go on into much more detail and start looking at spectra and things like that and comparing them to ensure the method is working well. But now that we have this in FastEddy, this gets us a long ways towards moving, again, out of the idealized scenario regime and into more realistic simulations. So this is just to bring back the point that for transport and dispersion simulations, the cell perturbation method and the skin temperature physics extensions are absolutely key to these kind of studies and these kind of simulations. You can see from the transported plume just how different things look when you have resolved turbulence and you have proper surface forcing. So, a little bit of a single GPU performance assessment by domain size. In the y-axis, we're looking at time steps per second. So this is how many time steps we can accomplish per second of wall clock time as a function of domain size. And I just use the x-axis as number of total grid points in the domain. This is again on the NVIDIA Pascal GP100. And we were pleased to see that we can achieve thousands of time steps per second for order 10,000 grid points, which is not a huge domain. But thousands of time steps per second says you're taking milliseconds to do a time step. That's pretty fast. I don't care who you are. For domain sizes of, say, 100,000 to 1 million cells, we achieve tens to hundreds of time steps per second. And it's nice to see that even into the regime of tens of millions of cells on a single GPU, we can still do better than 1 time step per second. So that's a lot of math occurring in a relatively small form factor with FastEddy accelerated on the GPU. So let me just go back one. So we looked at that and we saw, that's pretty good performance. Are there any sort of little things we can do to get better, to squeeze just a little bit more out of it? And this was a bit of work done by Alessandro Fanfurio, who I mentioned earlier, where we said we would like for the GPU not to have to wait on the CPU to write results to disk whenever we want to dump the state of the simulation. And so what Alessandro implemented is a little double buffered I/O approach. So what we're looking at here is NVIDIA's NVProf performance analysis tool. And what I'm pointing out is these big blocks of color you can think of as really the GPU doing work. And the more contiguous those blocks, the better. Okay, but these gaps right here are where the GPU has sent some results to the CPU, but it's sitting and waiting for the CPU to come back from having dumped those out to disk and say, okay, GPU, you can now proceed again. And so with this double buffered I/O approach, we basically we say, GPU, throw your results into some memory block up in the CPU's memory space, and then just keep on running, keep on computing, because you already have the state information. You can just continue with the simulation. And so what we see is that each of those blocks can now collapse because the CPU is concurrently writing to disk while the GPU continues its simulation. And so for this small problem size, we're seeing something along the lines of a 10% performance gain. Where this really helps is when we're doing the larger simulations, and we have quite a bit of compute, and dumping the state takes quite a bit of time, and those two things can overlap very nicely. So some more FastEddy progress, and this kind of came free to us in a way, so thank you, CISL. You procured Casper. And all of a sudden, we now had the availability of a Volta GPU. This is the latest generation. It's bigger, it's faster, and I'll talk a little bit more about that. So this is a slide where I'm going to look at the same performance. Well, I'm just going to state the same performance on the next generation overnight without even touching a line of code. Just by getting on the V100s, we either get 2 times faster or we can do 2 times the size of domain that we used to do. And that's primarily because as we went from the GP100 to the V100, we went from 54 streaming multiprocess units. Think of these like CPU cores of a GPU. We went from 54 to 80. In addition, our memory bandwidth on GPU went from 720 gigabytes a second to 900. And of course, the total memory on the V100 went from 16 to 32. So again, just overnight by CISL grabbing or procuring the new Casper partition with V100s, we could get twice as fast or twice as big on a single GPU without touching a line of code. So that was nice, and thanks again, CISL. So this, of course, was the announcement of the Casper architecture, which had, in particular, not just one GPU anymore, but now there were multiple GPUs per node. And so this was the first time when we had an opportunity with FastEddy to start looking at what could we possibly do with multiple GPUs. So this is a single GPU simulation, neutral boundary layer. You're looking at kind of turbulent structure over a domain of, say, 55 kilometers by 25 kilometers. So this is akin to the verification and validation scenario I showed you before. We can fit that on a single GPU. Well, in taking a naive approach to stacking together multiple GPUs, we could now do 200 and something kilometers by 80 something kilometers, a massive, massive increase. And this is all because each red square, you can think of just like CPU domain decomposition. This is horizontal domain decomposition, and each red square is one GPU running that original simulation to its fullest extent. That's just sort of a zoomed out picture of one block. So that's a massive upgrade. The way we did that was initially a really naive correctness first approach. We would take all 5 of our prognostic fields in FastEddy and send them from the device, the GPU, up to the CPU. That costs time and it's data movement. Then each MPI rank, each CPU, would fill some send buffers, perform some sort of standard MPI asynchronous non-blocking sends and receives to do a halo exchange, and then the receivers, the receiving CPUs, would send back down to the GPUs so that they could fill their halo cells and then take the next time step. Well, performance was pretty poor as expected. We went from this really fast single GPU implementation to a rather slow multi-GPU implementation. But we knew it was naive and it was not the best way to do it, but we wanted to make sure we could be correct first. So the nice thing is, while performance was not good yet, it made us realize, well, we can do really massive, massive LES domains. So we're no longer limited by the memory constraints of a GPU only has 32 gigabytes of memory. Okay, now we could start talking about some of the large sort of heroic LES simulations that we see performed more in the research realm. But we can do this on far fewer GPUs. So we decided to take a second crack at that most recently. and to try and exploit direct device-to-device communication. So this is where a GPU sends its Halo cells directly to another GPU that needs them. This could be done through asynchronous, non-blocking sends and receives with the MPI API, but CUDA-aware, or I should say MPI-aware CUDA, will wrap a regular MPI I-send, I-receive in such a manner that you can give that function device pointers. That's pointers to GPU memory. And under the hood, two mechanisms, one called GPU Direct for on-node device-to-device communications. This is when you have two GPUs on the same node. Or RDMA for off-node GPU communications. One of those two methodologies will be slipped in underneath the MPI and sort of take care of that for you. In addition, rather than pass full fields, we said, hey, let's just pass the ones we need. We don't need to pass full fields. So what we see, just very, very recently with this, is that we can now scale what looks like better than perfectly across the 8 GPUs of a single node. And the reason it looks better than perfect is because the baseline, the single GPU case, we're putting as large a simulation as we possibly can on a single GPU, and we are somewhat limited by bandwidth when our domain size gets super big. And so what you get when you then scale, do a strong scaling and look at, well, now when I pair GPUs or have 4 or 6 or 8, is something that looks super linear, but it's really not. It's not super linear. It's quite good, though. We strong scale very, very well across GPUs. This was early timings for 28 million grid point simulations, so that's 7 times bigger than the original sort of simulations I showed you early on. Our hiccup is, right now on Casper, the off-node GPU to GPU device transfers are not performing well at all. They are an order of magnitude slower than on-node. Now, Casper itself has what's called NVLink between GPUs. This is a 300 gigabyte per second bridge for data to go across. I'm not entirely sure, but I believe the path to a CPU and then consequently the GPU on another node has to go through PCIe, which is in an order of magnitude slower. So what that means is scaling to many nodes that require, many GPUs across multiple nodes is going to be a challenge for a bit, and we're going to need to see if we can come up with some ways to be even smarter about our Halo communications to try and compensate for the fact that they're sort of, actually it reminds me of the Eisenhower Tunnel where it necks down to 2 lanes all of a sudden and everybody has to slow down. If we have to go across PCIe, that's gonna be a bottleneck. Alternatively, there are other architectures out there like the Power 9s that we see in Summit and Sierra, the big DOE GPU machines that have NVLink 300 gigs a second right to the CPU. And we may find that if we get on an architecture like that, now we can scale to many, many GPUs without that big bottleneck of necking down before the Eisenhower Tunnel. So, can you wait for questions till the end? Okay, cool. So let me talk about where we're going now. And with FastEddy, I think this year has been about moving out of sort of the idealized toy code, newly developed. I wouldn't have ever called FastEddy a toy code exactly, but we were very much living in the idealized world, purely research-oriented. Where we want to go is to fill a forecasting gap. We have climate forecasting. We have regional numerical weather prediction. That's all faster than real time. What does not exist is microscale forecasting, and particularly in urban environments. So we've introduced flow obstacles to FastEddy, and they're modeled through a volumetric body force, so it's a drag. The approach is computationally very efficient and allows us to use uniform grids, but what you can see from these two simulations on the left is a convective boundary layer where there is lots of buoyancy-driven turbulence, and while the flow is forced to go around the obstacle, what you can see is that really the turbulence of the boundary layer itself dominates the process. And conversely, on the right-hand side, we're looking at a stable boundary layer, again, where turbulence is being kind of constantly damped, even if it exists. And what we have is some very interesting consequences of that obstacle in the flow path, where we essentially develop what's called horseshoe vortex. It's well known in sort of computational fluid dynamics for flow past an obstacle, where the flow is being diverted around the obstacle, and that induces vorticity, which pulls up cool air from down low. So we're working right now on validation of FastEddy with these obstacles. In particular, we're looking at a wind tunnel scale. So there was a set of experiments published by Casper et al. In Boundary Layer Meteorology 2006, where they had a wind tunnel and an array of cube obstacles. And so far with our early work here, FastEddy shows excellent agreement for both mean and turbulent profiles for this scenario. So it's sort of step one in validating an urban environment capability. Step two is to look at atmospheric scales. There was a field campaign in Oklahoma City called the Joint Urban 2003 Field Campaign. And so we currently have the building morphology data from Oklahoma City, and we're working from sort of the published literature on that field campaign right now to prescribe forcing conditions and do some simulations that we can compare against that field data from that campaign. What we're looking at here is a vertical YZ plane, so that's Y along the x-axis and sort of Z along the y-axis. We're looking at span-wise or streamwise velocity, so the wind's blowing sort of your left to right, and we can see in the early regions of the domain, we see the atmospheric boundary layer develop due to the cell perturbation method. This is a limited area domain simulation. And then as we come into contact with the urban canopy, the buildings themselves are causing an urban boundary layer to develop. And you see these sort of red flashes where these are actually recirculation zones, where the wind is actually on the lee side of a building, curling around and traveling back upstream, producing some really interesting flow features. One more, just to show you. I could sit and stare at these all day. We're looking at horizontal slices now at a height of 7.5 meters, I think. So these simulations were run at 5-meter resolution over a domain that spanned 2 kilometers from west to east and 3 kilometers from south to north. The left panel is streamwise velocity component, so the flow is coming from the south and going past the Oklahoma City downtown region. The middle panel is span-wise velocity, so this would be the sort of left-right component of velocity. And the far right panel is vertical velocity. And what we can see is that basically, with the combination of the surface forcing conditions we've added and the cell perturbation method to instigate turbulence, we think we're going to have some really nice agreement with these Oklahoma City field campaign results. And we can start tackling this gap of microscale forecasting in an urban environment. I'll say that the speed, we could push towards that because the performance is going to have a ways to go. We need to keep pushing. We need to scale beyond just one single node's worth of GPUs. We're going to need to get to many more in order to be faster than real time at these fine spatial resolutions. There's just no two ways about that. The GPUs themselves are fast, but just the same way that numerical weather prediction mesoscale codes right now get faster than real time on CPUs, they do that by not really pushing each CPU to its maximum potential. They put little amounts of work on each CPU and then run on many CPUs. We're going to have to do the same thing with GPUs if we want microscale to be faster than real time. So with that, I'll close and kind of just summarize with this. In the last year, FastEddy continues to mature with respect to underlying verification and validation exercises, the physics, the numerical techniques, and our GPU-accelerated simulation capabilities. FastEddy's got plenty of challenges and opportunities remaining. One is performant off-node device-to-device communications. 2, a prognostic TKE-based turbulence closure for more accurate subgrid turbulence parameterization. Another place we should look is acoustic wave filtering so that we're not fully compressible and we can relax that CFL time step, which will give us gains on faster than real-time performance. And the last one I've written down is just addressing sort of yet to be determined stakeholder needs from modeling and analysis like this, which is very new to them. I think we'll see a lot of artificial intelligence, machine learning type approaches, especially since we're running on GPU anyways. And as well, visualization goes hand in hand with what GPUs do best. So with that, I'll say thanks to CISL and thanks for attending and answering any questions.